Hello everyone, welcome to topic 1.1, moles and molar mass. We have the following learning standards that are listed here below. We are specifically for this section going to cover these essential knowledge components. Stating one cannot count particles directly while performing laboratory work, thus there must be a connection between masses of a substance reacting and the actual number of particles undergoing chemical changes. Also, that Avogadro's number provides the connection between number of moles in a pure sample of a substance and the number of constituent particles, or formula units of that substance, and that expressing the mass as an individual atom or molecule in atomic mass units is useful because the average atomic mass in AMU of one particle, atom, or molecule, or formula unit of a substance will always be numerically equal to the molar mass of that substance in grams. Thus, there is a quantitative connection between the mass of a substance and the number of particles that substance contains. So our notes are going to address those three today. So it is impractical to count the atoms as they are so small. So in chemistry, we can count atoms by weighing them or measuring them in some other way. We need to convert the measurements that we make into our numbers of atoms so that we can be sure to react the right amounts of materials. Atomic masses are measured in atomic mass units, or AMU, which is a relative unit based on the carbon-12 isotope being assigned a mass of exactly 12 grams per mole. A mole is a term used to describe a group of atoms containing 6.022 times 10 to the 23rd atoms. Chemists use moles to discuss the amounts of atoms because using the actual number of atoms is such a large number it is often impractical. You can calculate the mass for 1 mole of a substance by referring to the periodic table to find the average atomic mass of each atom and then adding up the total mass for the formula. We have an example, we have an outline of how to do that here, and we have an example in the box. So for dinitrogen tetroxide, you list the atoms and then you count. So from the subscripts, we get the number, and then you find the mass of each one from the periodic table. They are using a different periodic table than what is provided on the AP test and what is provided to you in class. Those two are the same. This is just one that goes out to more significant figures, but they work the same. So we find the periodic table masses for each atom, and we multiply by them together to get another number, and then we add them together to get the total molar mass for the compound. Molar mass can be used as a conversion factor to convert between moles and grams. It is unique for each sample because the ratio of each type of atom and the types of atoms present vary. Avogadro's number, or 6.02 times 10 to the 23rd particles per mole, is the conversion factor to convert between the number of particles and the number of moles. And going back to your first year of chemistry, we discussed how particles, and I did this with my classes, and don't judge my umbrella. We're going to fix it a little. Particles is a big umbrella that covers and encompasses the terms molecules, atoms, formula units, ions, and we can also add compounds in there. In chemistry, when we say particles, we can mean any one of these depending on what that specific substance is. Okay. And then we can also, from here, combine these two conversion factors. And we did this in your first year chemistry, where if we have mass, and that's measured in grams, we can convert that into moles, and from above, we see we can use the molar mass for that. And remember that the molar mass has units of grams per 1 mole, so we use dimensional analysis to make sure those units cancel out, and we'll go over that in the practice problems that follow. And from the mole, we know that we can go to particles, any type of particle, because of this umbrella over here, right? So any type of particle or particles, and we use Avogadro's number. And remember that that has units of particles per 1 mole. Okay, so now let's look at how can we use this. Remember that if you can go one direction, you can flip that conversion factor and go another. So let's put this into practice. So how many moles of lead to iodide, or PbI2, are there in 25-gram sample? So we are starting with 25 grams, and it wants us to go to moles. So we're going grams into moles. So that is this part here. Okay, that tells us that we need the molar mass of lead iodide. So we should calculate that first. So PbI2, we look up lead, and we see that it is 207.2, and then we have 2 iodine. And I'm going to shorten how much I write, because I am tight on space, and you are probably too, and it's not liking me. Okay, so now I calculate this, and I should get 461.0 grams per 1 mole of lead to iodide. Okay, so I can now use that to change 25 grams into moles. So I start with what I'm given, and I'm hoping that this is review, but we're going to make sure that we know what we're doing. And I need to change it into moles. Now in dimensional analysis, I put the unit I don't want on the bottom because I need it to cancel out, and I put the unit I need to have at the end, or I need to go into on the top, so I change it. And this is my conversion factor, moles to grams. And I know that the molar mass is a number of grams, which in this case is 461 grams of iodide is for 1 mole. Okay, and so now I run that calculation. I multiply across the top, and I divide by the bottom. That cancels my grams, and I am left with 0.0542. 3 significant figures because I have 3 sig figs here and 4 on the bottom, so I'm using 3 sig figs, the smaller number, moles of PbI2. My next one says how many atoms of lead are in the sample. So this is a compound or a formula unit, so I have moles. I need to go to the compound or formula unit, so and then I can go to atoms, because lead is in this compound. We're going to see that since it's a 1-to-1 ratio, it's easy, but we still need to check that because it is not always going to be a 1-to-1 ratio. So setting this up, we're going to use the moles we found in the previous part, so 0.0542 moles of lead iodide. And we have to change that into compound first. So we bring moles down. And then and then we have a compound of the lead iodide. Okay. From there, we can take the compound of lead iodide and we can relate that to how many atoms of lead are in that compound. Okay, so we're going to fill in our conversion factors first. So for here, this one should make sense, this first conversion factor, because we bring this down, and we can't change our substance before we change our unit. So we change our unit into compound. So 1 mole of a type of particle is 6.022 times 10 to the 23rd of that compound. Okay, that's Avogadro's number. We can use that as a conversion factor because a compound is a type of particle. Then we come over here and we have 2 types of particles, so we are not going to use Avogadro's number. We already used it, we can't use it again. But we can say that in one of these compounds, we see 1 atom of lead because there is no subscript, so we assume that there is 1. Okay, if we were talking about iodine instead, this number would be 2. But since we're talking about lead, it is a 1-to-1 ratio. And yes, technically we don't need it, but we are showing all of our work so we get the thought process down and understand the concepts behind this. So that way we can apply it to things that aren't as easy. So, canceling out, we are left with atoms of Pb, or lead. And then multiplying by the top, and then dividing by the bottom is boring because it's all 1. We should end up with 3.26 times 10 to the 22nd power atoms of lead. 3 significant figures because that is what we start with. These are definitions. They technically have infinite sig figures and you don't use them. Okay, now on to the we do. We have a 0.02 or 0.244 gram sample of calcium carbonate, and it was recovered from a sample of hard water. How many formula units, now that is a type of particle of calcium carbonate were in the sample. So we have grams of calcium carbonate, and we want to end up at formula units. I'm going to write FU, but I mean formula units and not anything strange or offensive. Okay, but writing all the formula units out is really long. So we're using the academic meaning and not any other sort of meaning. So I want to go between these two, and I see that from our notes that we can go to moles first because both of these are related to moles. And then my other thing is I need to figure out how much calcium carbonate weighs. So I need to add calcium plus carbon plus 3, and I'm going to put the oxygen in parentheses so we can see that it's probably oxygen. So I'm going to look up their molar masses. So calcium is 40.08, carbon is 12.01, and then we have 3 oxygen at 16.00. When I run this math and add them all together, I end up with 100.09 grams per mole. And so that is my molar mass for calcium carbonate. So now I have everything I need to do. I want you to pause the video here and try this first on your own, and then run it yourself and see if you got the correct answer after. Okay, so now you should be able to see that we put down what we're given first, we change it into moles next, and then into formula units. Okay, from there, I don't know if you guys can see my pen, but we're just going to hope. From there, we can drag units diagonal so that they do cancel and fill in our conversion factor. First our molar mass, and then Avogadro's number, remembering that Avogadro's number, the actual number, goes next to the particle unit, which in this case is formula units, and it's always for 1 mole. Okay? The only time it won't be 1 mole is if we're doing mole-to-mole ratios, where it's moles over moles. That is the only time it will not be 1. Then we run the math, and you should have gotten 1.47 times 10 to the 21st power formula units of calcium carbonate. Okay. Additional practice problems are here as you go through. Okay, make sure you work these out. And an answer key will be provided for you to check your work in class. Thank you, guys.